Hi, I'm Tanish, and today we're going to learn about inverses. So, before we get into inverse matrices, I want to first teach you what an identity matrix is. So, an identity matrix is essentially just a square matrix, which means the number of rows and columns in this matrix are equal to each other. But every single value in this matrix will be zero except for the main diagonal. So, if you look at this matrix I've drawn here, this is exactly what I told you. Um, this is a square matrix. Every value in this is a zero except for the main diagonal, which is the diagonal that goes from the top left to the bottom right. So how is this useful? Well, if you have another matrix, so let's say we have matrix A. Now, matrix A is a 3 by 3 matrix. So if we were to multiply A, and let's call this matrix B, let's call this B, matrix B. If we were to multiply A times B, then the reason it's called the identity matrix is if once we multiply them, we'll still get the matrix A. But if you do it the other way around, it also works the same way. Normally, when you multiply two matrices, if I have another matrix C, which is also a 3 by 3 matrix, if you were to multiply them out, then this would not be the same thing as if we switch the order of where we're multiplying. So the order matters when you're multiplying, well, matrices specifically. But for identity matrix, that doesn't matter. So the order doesn't matter when you're multiplying for an identity matrix. So this will still, if you do B times A, this will still be equal to A. So that's the point of an identity matrix. It's so that you get the same matrix if you multiply it to another square matrix of the same dimensions. So identity matrices for 2 by 2 is 1 0 0 1. For a 4 by 4, which would be 1 0 0 0 0 1 0 0 0 0 1 0. There's not enough space. 0 0 0 1. So this is for 4 by 4. In every case, you can see the main diagonal having ones and the others are just zeros everywhere else. With that being said, let's get into inverses. So if what is an inverse exactly? So if we have a normal arithmetic value, let's say 5, its inverse is just the reciprocal of this value, which just means 1 over 5. So if you have a normal number, its reciprocal will be 1 over n, except that n cannot equal to 0 because 1 over 0 will just cause problems. Um, so inverses aren't like finding you can't really find a reciprocal for matrix. But I'll tell you how to find inverses later. But so essentially, if you multiply 5 times its inverse, you get 1. Well, if you have a matrix, let's say we have matrix A, which is an n by n matrix, and we have its reciprocal, which will since matrix A is an n by n matrix, its inverse would also be the same dimension, so it'll be n by n. So this only that you can only find the inverse of a square matrix. So that means A has to be a square matrix to have an inverse. So with that being said, if you multiply A times A inverse, you get the identity matrix. So the identity matrix is basically is 1 0 0 or 0 1 0 all the way to the how many rows and columns it has, right? So this will be n by n, right? So the identity matrix in this scenario is just a matrix with all zeros except for the main diagonal, which will be ones, and it should have the same dimensions as the as as A or and A inverse. So if you really think about it, the identity matrix is kind of like 1, because if you multiply any number by 1, 5 times 1, you get the same number. So in that case, it still works for matrices. So if you multiply any matrix by the identity matrix, you get the matrix itself. So if you can multiply A times its inverse and get the identity matrix, what if you multiply its inverse like this times the original matrix? Because remember, matrices, the order matters when you're multiplying. So you do get, in fact, the identity matrix. So the definition of a inverse of a matrix is they both have to be square matrices of the same dimension. So in this case, it was just an n by n matrices. And if you multiply them together, A should and times its inverse should be equal to the identity matrix. And then A inverse times times A should be also be equal to its inverse. So to its identity matrix, sorry. Now let's try to find the inverse of a 2 by 2 matrix. This method only works for 2 by 2 matrices, so don't try it with anything else. So let's say A inverse is, for a 2 by 2 matrix, is 1 over the determinant of A times the matrix, where we from the original matrix we basically switch this diagonal. We put the D over here and we put the A over here. And then so let's do that real quick. So we put the D here and the A here, and then we make these two values negative. So it would be negative B times negative C. So let's try an example with this. Let's say we have matrix B, which is equal to 2 times 2, negative 3, 1, negative 4. So B inverse will be equal to 1 over the determinant of B times the times, let's do this. So we take the 2, we put it here. We take the negative 4 and we put it here. We basically swap it, negative 4, 2. And then we multiply these two values by negative 1. So 3 and negative 1. Now for the determinant, you should already know how to find the determinant of matrices. If not, you could check the previous video I've made on that. But for the determinant of B, is just the 2 times negative 4 minus 1 times negative 3. So 2 times negative 4 minus 1 times negative 3. So this is equal to negative 5. B inverse is 1 over negative 5 times this matrix. Define matrix A as a n by n matrix. That means it's a square matrix. So since it's a square matrix, we should be able to find the inverse of it. So the general formula for the inverse of a matrix is A inverse, which would be 1 over the determinant of A times the adjugate of A. Now, if you compare this to the formula for inverse of a 2 by 2 matrix, let's do that real quick. I'm gonna pull the formula up. So this is the formula for a 2 by 2 matrix. This is only for a 2 by 2 matrix. Only 2 by 2 matrices. Sorry. So I want you to compare these formulas and try to find the difference. So we still have 1 over the determinant in each of these formulas, except in this one it's being multiplied to the adjugate of A, but this one it's multiplied to a weird matrix. We basically just like did some swapping and multiplying by negatives. So I guess a logical conclusion is if you were to use this formula on a 2 by 2 matrix, right? Then you'd realize the adjugate of A only for 2 by 2 matrices is this weird matrix that I found here. So for a 2 by 2 matrix, the adjugate of A is equal to a lot of swapping out. So D, negative B, negative C, and A. This is only for 2 by 2 matrices. If you just like finding the adjugate is very different when you have bigger dimensions of matrices. But for a 2 by 2, it's as simple as just be swapping, and for negative, just multiplying by negatives, I guess. We have the matrix A defined as a 3 by 3 matrix which contains these well, good real numbers. So this is a 3 by 3 matrix. So we should be able to find the inverse of this matrix. So the normal equation, finding the normal equation for finding the inverse of a matrix is A inverse is equal to 1 over the determinant of A times the adjugate of A. Finding the determinant of this matrix shouldn't be a problem. We should already know how to find the determinant of this. But finding the adjugate is not something I've told you yet. So let's let's just try to find how to get the adjugate of A. Now, this probably seems like a long process, but anything with matrices is just like it takes a lot of arithmetic skills. So when you're trying to find the adjugate of A, we have to convert this matrix right here into, first you gotta convert it to the matrix of minors, and then you gotta turn it into the matrix of cofactors, and then you can find the adjugate. So that's a it it, it takes a long time. Unlike if it's a 3 by 3 matrix, it's easier, but as the dimensions get higher and higher, it just takes longer and longer. So let's first convert to the matrix of minor. If we let's to do that, we if you remember, if you have watched my previous video, when you try to find the determinant of a 3 by 3 matrix, you chose the value, and then you canceled the row and the column that had the value in it, right? So since if I choose 4 over here, the row that has it is the first row, and the column that has it, it's the first column. You cancel them out, and then you found the determinant of this, and you multiplied that with the 4. It's all that mess happened, right? So when you're trying to find the matrix of minor, you have to have the first step. So you choose the value, and you cancel the row and column, and you find the determinant of the remaining values. Since we chose the value that's in the first row and column, we put the determinant of that value, 3, 9, 1, 3, in the first row and first column for the matrix of minor. So we gotta do this step for all the values in this matrix, and that's why I think finding inverses is kind of annoying. But you gotta deal with it. So I choose the second value and cancel the row and the column that it's in. So the remaining values would be 5, 9, 2, 3. So you got to put in order. Order definitely matters. So the first value here is 5, there's a 9, there's 2, and there's a 3. Um, oh, let's 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 try the next value. It's the 7, and that would be 5, 3, 2, 1. And now I gotta keep doing that for the other ones. I'm gonna do a couple more, and then I'm gonna skim through this process. So I'm gonna do the 5, and then we have the remaining values 2, 7, 1, 3. Determine 2, 7, 1, 3. And I'm gonna do, let's do the 2 over here. Cancel the rows for 2, and then we have 2, 7, 3, 9. So let me just skim through this entire process. We have the 4, 7, 2, 3, 4, 2, 2, 1, 4, 7, 5, 9, 4, 2, 5, 3. Honestly, I think the hardest part of this entire process is like finding the determinant of all of these things. It gets harder for if you're trying to find the determinants of 3 by 3 matrices, because you can't like do the easy method of just like multiplying the diagonal and subtracting from the other diagonal. That's the benefit of finding the determinant of a 2 by 2 matrix. So if I solve this entire thing out, I should get 0, -3, -1, -2, 0, -3, 1, and 2. Now that we have this, if this is our matrix of minors, we got to convert this matrix of minors into the matrix of cofactors. So when you're trying to find the determinant of a matrix, we had to use the pattern for cofactors, and this is really where you have to use it a lot more. So in the previous video, I defined the pattern for cofactors. If you start with a plus, then you go with the minus, then plus, minus, plus, minus, all the way to the number of rows and columns you need for the pattern. In this case, since this is a 3 by 3 matrix, we need a 3 by 3 pattern. So I'm going to stop at this plus. You go minus, plus, minus, plus, minus, plus. Let me make this fit. So this would be our pattern of cofactors for the matrix of minor for the 3 by 3 matrix. So if we were to apply that, it's essentially just multiplying by +1 or -1 depending on the sign depending on if it's the positive sign or the negative sign. So if we were to apply this one onto this, we should get this matrix: 0, 3, -1, 1, -2, 0, -3, -1, 2. So what I did was like positive 1 times 0, -1 times -3, which is 3, +1 times -1, -1, -1 times -1, which is 1, and onwards. The last step is to find for the adjugate of A. So to find the adjugate of A, we basically highlight. Let's highlight the main row, main diagonal, and since we highlight that, we swap the values in this matrix like a mirror. So if we have the 3 over here, we swap it with the 1 here, like it's a reflection in the mirror. So so we're just basically like taking this and we're moving it here. We take this value, we move it here, and this value we move it here. So kind of like reflecting off a mirror. We were to do this. We keep the main diagonal. We don't do anything with the main diagonal. And we swap the values. This 3 gets swapped out for the 1. So the 3 goes here, the 1 goes here. This -1 gets swapped out with the -3. The -1 goes here and the -3 goes here. And the 0 gets swapped out with the -1. So the 0 goes here and the -1 goes here. Now this is the adjugate of A. The only hard part of finding the adjugate is the matrix of minors. Otherwise, it gets simpler towards the end. Now that we have the adjugate of A, all that's remaining is to find the determinant of A to finish off trying to find the inverse of A. So the determinant of A is pretty simple. You have to use the pattern of cofactors. Remember that. Let's do this real quick. So minus plus, and apply the first row onto this row. 4. Then I'm just gonna quickly skim through this. 3, 9, 1, 3. Next one would be, since we applied that, it'll be 4, -2, 7. So this one would be plus -2. If you don't know what I'm doing, you probably want to check out that video that I previously mentioned on finding determinants. It probably help understand what I'm doing. 5, 9, 2, 3 plus 7 times determinant of 5, 3, 2, 1. Before you solve this entire thing out, Let's just look at these determinants that we have over here. The first determinant is 3, contains 3, 9, 1, 3 over here. But if you look here, you have that same determinant right over here, right? And if we solve that out, we got 0. So we just don't have to find the determinant of this entire matrix all over again. We could just use what we have over here, right? Because it kind of makes sense how we did this, right? We use the same method for finding the determinants when we found the values for the matrix of minor, right? So we could use those values for to go back and use it for the determinant version. So essentially, it's like a cheat hack. It's just a hack on solving the determinants if you have the matrix of minor. So this next matrix we have here, it also correlates with the matrix over here. This matrix over here correlates to the matrix over here. So that was 0, -3, -1. So we do 4 times 0 plus -2 times -3, -2, right? And then there's -1 remaining, so plus 7 times -1. If we solve this out, we should get -1. And yes, this is the determinant of A. So A inverse is equal to 1 over -1 is still -1, so we can just write it out like this, times the adjugate of A. Now the adjugate of A we found was, well, let me, hold up, just gonna have to write it out like this, so -1, let's see, 0, 1, -3, yeah. 3, 2, 3, -2, -1, 3, -2, -1, -1, 0, 2. It's a little messy, but bear with me. So we just simply multiply it out and we get our inverse. And that's how you find the inverse of matrices.